we are going to discuss about interconnection of operations on systems. So first we are going to study about the system. A system is a mathematical model of a physical process that relates the input signal to the output signal. It may be viewed as an interconnection of operations that transforms an input signal into an output signal with properties different from those of the input signal. The operator H denotes the action of the system. A continuous time system is a system in which continuous time input signals are applied and results in continuous time output signals. When the application of a continuous time signal x of t to the input of the system yields the output signal y of t, which is equal to h into x of t. The block diagram representation is as shown here. We can see x of t is the input and y of t is the output. Similarly, in the discrete time domain, the output signal y of n from a system for the input signal x of n is given by the relation y of n is equal to h into x of n. The block diagram representation is as shown below. X of n is the input and y of n is the output. The operator s to the power k denotes a system that shifts the input x of n by k units to produce an output signal to x of n minus k. So x of n is the input, y of n is the output, s to the power k, which denotes the system which shifts the input x of n by k units. Next we have moving average systems or MAS. The system output is basically a weighted average of the input signal. Then y of n is equal to 1 by m plus n summation k is equal to 0 to m dk into x of n minus k, which is equal to, that is expanded, v naught into x of n plus v1 into x of n minus 1 plus v2 into x of n minus 2 plus v3 into x of n minus 2 plus so on into vm x of n minus n divided by m plus 1. Consider y of n is equal to x of n plus x of n minus 1 plus x of n minus 2 divided by 3. There are two reasons to name it as moving average. First one is y of n is the average of the sample values of x of n minus 1 and x of n minus 2, and the value of y of n changes as n moves along the discrete time axis. Then h becomes 1 divided by 3 into 1 plus s inverse plus s to the power minus 2. There are two ways of representation as shown below. First one is cascaded as shown in the first diagram, and the second one is parallel connection as shown in the second diagram. Next we are going to study about properties of system. So first one is stability. The system is said to be bounded input, bounded output, that is BIBO, stable if and only if bounded input results in a bounded output. A stable system is one in which signal inputs lead to response that do not diverge. There are some conditions for BIBO. First one, consider a continuous time system whose input-output relation is described by y of t is equal to h into x of t. The operator h is BIBO stable if the output signal y of t satisfies the condition y of t less than or equal to m by less than infinity for all t. Whenever the input signal satisfies the condition x of t less than or equal to mx less than infinity for all t. Both mx and my represent some finite positive numbers. Similarly, in discrete time domain, the operator h is BIBO stable if the output signal y of n satisfies the condition y of n less than or equal to my less than infinity for all n. Whenever the input signal satisfies the condition x of n less than or equal to mx less than infinity for all n. Both mx and my represent some finite positive numbers. For example, show that the moving average system y of n is equal to 1 by 3 into x of n plus x of n minus 1 plus x of n minus 2 is a BIBO stable. Assume that x of n less than or equal to mx less than infinity for all n. Using the given input-output relation, y of n is equal to 1 by 3 into x of n plus x of n minus 1 plus x of n minus 2. Y of n is equal to 1 by 3 into x of n plus x of n minus 1 plus x of n minus 2 less than or equal to 1 by 3 into x of n plus x of n minus 1 plus x of n minus 2, 1 by 3 into mx plus mx, which is equal to less than or equal to mx. Hence output is bounded for the bounded input. Hence the system is stable. Next we have memory. A system is said to process memory if its output signal depends on past values of the input signal. In contrast, the system is said to be memoryless if its output signal depends only on present value of the input signal. For example, a resistor is memoryless since the current I of t flowing through it in response to the applied voltage V of t, defined by I of t is equal to 1 by R V of t, where R is the resistance of a resistor. An inductor has memory since the current I of t flowing through it is related to the applied voltage V of t as follows. The moving average system described by the input output relation I of t is equal to 1 by L into integration minus infinity to infinity V of t into dt. Since it depends on past values of the voltage, inductor has memory. The moving average system described by the input-output relation Y of n is equal to 1 by 3 into x of n plus x of n minus 1 plus x of n minus 2 is memory, whereas Y of n is equal to x power of n is memoryless. We have one note. A system is said to be having memory if the current output depends on the future values of input and output. For example, y of n is equal to y of n plus 1 plus x of n. Y of n plus 1 is equal to y of n minus x of n. Next property we have causality. A system is said to be causal if the present value of the output signal depends only on the present and or past values of the input signal. For example, the moving average system described by the input-output relation y of n is equal to 1 by 3 into x of n plus x of n minus 1 plus x of n minus 2 is a causal system. If the output signal of a system depends on future values of the input signal, then it is known as non-causal system. For example, y of n is equal to 1 by 3 into x of n plus 1 plus x of n plus x of n minus 1. Next, we have invertibility. The system is said to be invertible if the input of the system can be recovered from the system output. In the first diagram, we can say x of t is the input for system 1 and y1 of t is the output of the system 1, and that is applied as input to the system 2, and y2 of t is the output of the second system, which is equal to x of t. Or x of t is applied to system 1, y1 of t is the output, then h inverse is the system 2, output is x of t. X of t is input to y of t, which is equal to 2 into x of t. Output is y1 of t, that is applied as input to the second system, that is w of t is equal to y2 of t divided by 2, or y2 of t is equal to x of t. Next we have time invariance. The system is said to be time invariant if a time delay or time advance of the input signal leads to an identical time shift in the output signal. The characteristics of a time invariant system is that they do not change with the time. Consider y of t is equal to h into x of t. The input signal x of t is shifted in time by t0 seconds, resulting in the new input x of t minus t0. This operation may be described by writing x of t minus t0 is equal to s to the power minus t0 into x of t, where the operator s of t0 represents a time shift equal to t0 seconds. If y of t is denote the output signal of the system produced in response to the time shifted input x of t minus t0, then yi of t is equal to h into x of t minus t0, which is equal to h into s to the power minus t0 into x of t, which is equal to h into s to the power minus t0 into x of t. So x of t is the input to s to the power minus t0, output is x of t minus t0, which is applied as input of second system, and output is yi of t. If y of t represents the output of the original system shifted in time by t0 seconds, then yi of t is equal to h to the power minus t0 into y of t, which is equal to h to the power minus t0 into h of x of t, which is equal to h to the power minus t0 into h into x of t. Let the input I of t be shifted by t0 seconds yielding I of t minus t0. The response yi of t of the inductor to I into t minus t0 is yi of t is equal to 1 by L integration minus infinity to t I of t minus t0 into d term. which is equal to 1 by L integration minus infinity to t I of tau into d tau. So I of t is the input to the first system, and output of the signal is 1 by L integration minus infinity to t I of tau into d tau. That is the input to s to the power minus t naught, and output is 1 by L minus infinity to t minus t naught to I of tau into d tau. For y I of t is equal to 1 by L minus infinity to t I into tau minus t naught into d tau, then tau is equal to tau minus t naught, or d tau is equal to d tau. Y I of t is equal to integration minus infinity to t minus t naught I of tau into d tau, which is equal to y naught of t. In mathematical terms, y I of t is identical to y naught of t, hence time invariant. Similarly, in discrete time domain, t is replaced by n. If yi of n denote the output signal of the system produced in response to the time shifted input, then x of n minus n naught, if y naught of n represents the output of the original system shifted in time by n naught seconds. The system is time invariant if the outputs yi of n and y naught of n are equal for any identical input signal x of n. The discrete time system described by the input-output relation y of n is equal to r to the power unit x of n is not time invariant. Next, we have linearity. A system is said to be linear if it satisfies the principle of superposition. That the operator h represents a continuous time system, that the signal applied to the system input be defined by the weighted sum, where x1 of t, x2 of t, so on xn of t denote the set of input signals, a1, a2, so on and denote the weighing factors. The resulting output signal is written as y of t is equal to h into x of t, which is equal to h into summation I is equal to 1 to n ai into xi of t. If the system is linear, the output signal y of t of the system as y of t is equal to h into xi of t, where yi of t is the output of the system in response to the input xi of t.